Hello and welcome to this segment. We are going to be talking about Riemann sums. This is a slightly different approach to integration. To connect with what we did before, I will start by talking about how I can find approximate values of solutions to initial value problems. To fix our ideas, we'll work with a specific example. So let's take the initial value problem, f prime equals 1 over 1 plus x squared, f of 0 equals 0. We don't know how to calculate values of original function f, but we can use differential approximation to find approximate values. The idea is that I have this differential approximation. So if I know f prime of x, if dx is small, I can approximate value of f at x plus dx. Of course, this works well only when dx is small. So for the moment, let's ignore that. Let's just use this, try to answer question I raised just a moment ago. Well, I know what f prime of 0 is, or I know what f of 0 is. I want to find or approximate f of 1. So I'll just take dx to be 1. Put everything in this differential approximation. So that will give me this approximation. So f of 1 is approximately 1. Of course, this is very crude. Dx is not really that small. So how do we get around this? So what if I think of it as not trying to get f of 1 all at once, but finding values of f at intermediate points and work my way up, or as they say, bootstrap my way. I will estimate values of f between 0 and 1. Estimate the value of f at the next number. I will use my previous estimate and the differential approximation. So if I decide to do this in 4 steps, I will try to estimate f at 0.25, 0.5, 0.75, and finally get to 1. F of 0.25 would work the same way as this, except h is 0.25, which gives me 0 plus 1 over 1 plus 0 squared times 0.25, and that equals 0.25. Next, we will look at 0.5. If I use h equals 0.25 and x equals 0.25, then I get my differential approximation for the next, and that comes out to be 0.4853. And I use this approximation. This is my approximate value for 0.5. I put it in here, use that to find the differential approximation f of 0.75, and I continue like this all the way to f of 1. So I get a different answer, and it turns out this is a better approximation. F of 1 exact value is pi over 4. This is a better approximation because pi over 4 is around 0.78 something. Now I used only 4 steps here. What if I use more steps? We will come to this with examples later. Let's just write down what the idea is. Let's assume that I have an initial value problem where I'm given f prime of x and f of a. If I give me a different number for f of a, that will only change the function f by a constant. We'll keep it simpler and assume that f of a is 0. Then I decide I want to use n steps. We'll decide on what n should be later. So I divide the interval into n equals size steps and then bootstrap my way up just as we did before. So given f of a, I will take dx to be my step size h, use the differential approximation. That gives me the approximation f of a plus h equals 0 plus h times f of a. Now use this approximation for f of a plus h and use the differential approximation with dx equals h again. That gives me an approximation for f of a plus 2h. And then using f of a as my approximation for f of a plus h, I get another approximation for f of a plus 2h. And then continue like this all the way to the end. 0 in the beginning can be left out. So we get our approximation for f of b. H times f of a plus h times f of a plus h all the way to the end. Now as I make n larger, h will get smaller. So at each step, the error will be smaller, but I have more steps. So these two work in opposite ways. And the question is, will the total error get smaller, larger, or bounce around? It turns out, you can also look at this geometrically. A question that's completely different from initial value problems. So consider the problem of finding area of general regions, not bounded by straight lines. Algebraically, the simplest region would be those where only one side is curved. The simplest region to find areas of are rectangles. And assume that I have something like a rectangle, except that one side is a curve, not a straight line. Simplest such thing to deal with algebraically would be something like what's shown here. X-axis is one side, two vertical sides. The fourth side is a curve, a graph of a function. If I had a horizontal line for the fourth side, I would have an honest to goodness rectangle. Area would be length times width. If the fourth side doesn't differ very much from a horizontal line, that would still be a good approximation. But what if I have something that curves visibly? If I take thin strips though, then the curve doesn't really differ that much from a horizontal line. So for thin strips, that would still be a good approximation. That is, area of the strip is approximately the height of the strip times the width of the strip. Of course, I don't know what I should use as my height. I can use the height in the left, the right, somewhere in the middle. For now, let's just use the height in the left. If the graph goes down, this will be an overestimate. This is the graph of 1 over 1 plus x squared. Divide it into 4 strips, so each strip has width 0.25. The height at left is f of 0 for the first, f of 0.25 for the second. That is 1 over 1 plus 0.25 squared for the second, 1 over 1 plus 0.5 squared for the third. Value of the function whose graph this is at each of those numbers. So I find the areas of these rectangles, use it as my approximation for the strips, take the total. This sum is of course precisely the sum we get here because this is the area of the first strip, second strip, third strip, fourth strip. Now if you think about it as area rather than using differential approximations, it might be a better idea to use some point in the middle. So what it means is that I get a sum like this, but instead of using f of a plus h, f of a plus 2h, I will use the value of small f at some number in that interval between a and a plus h for the first one, a plus h plus a plus 2h for the second one, and so on. Use the height on the left, height on the right, height in the middle, or height at just some random choices. Any of these would be fine as approximation. But if you want to actually do the calculations, it's helpful to use one of these three where we use systematic choices, because then we can use our calculator or program a computer to do these calculations. Whereas if you do random choices, you have to make the choice each time. You cannot completely automate. But for theoretical purposes, it turns out that allowing random choices is a good idea. But since we are not really going to do proofs, we won't really use them. We will just compare the left height, right height, height in the middle, and see how they work. We will do that in the next segment.